equations, notice if I have a disjoint two sets A and B, two events A and B in a sample space, then the intersection's null, right? There's nothing in the intersection. So the probability of the empty set you earlier showed was 0. So this is just axiom 3. If these sets don't overlap each other. But if they do overlap each other, and you think of probability as computing the area of these regions, well, the area of the union should be the area of everything in A and B, so it's this area. The problem with that, however, is if you just add up the area of A and the area of B, is that you're counting this intersection area twice.
Right.
And so you want to remove it once.
Oh, okay.
Okay? So this is compensating for the overcounting of the intersection if it exists. In this case, it doesn't exist. But when it does exist, you need to get rid of that overcounting. Right?
But then in our Venn diagram, we do have an overlapping.
Yes. Yeah, that's the point, is in this case, we're looking at A and B more generally, where there's the possibility of overlap. So the special case is when there's no overlap, but we're now looking at the case, and maybe I should have made this clearer in the statement of this claim, but we're now looking at the case for any A and B with overlap or without overlap. This formula holds. If we don't have any overlap, then we're back with axiom 3, right? Because this part just goes away.
So where does A complement come in?
So when we do the proof, so we have this A union B, we've decided that this is in fact equal to A union A complement intersect B. And then we've also shown that, or decided that it was true, that B is equal to A intersect B union A complement intersect B. And so we want to use these two things to prove this.
So the little union in between the two parentheses, explain that again, why we have it there?
Because that's what makes this statement true. This is saying if we take A intersect B, which is here, and we combine it with A complement B, which is this stuff, we get B.
Okay. All right.
So here's a proof. My hint down below is we want to use axiom 3 and write down equations for the probability of A union B and the probability of B. And I'm referring to, let's use this. So we know that the probability of A union B is going to be equal to the probability of A union A complement intersect B. And that doesn't look particularly helpful, except that we earlier realized that A and A complement intersect B were disjoint. So we can rewrite this as the probability of A using axiom 3 plus the probability of A complement intersect B. And this is because A intersect A complement intersect B is empty. So this is axiom 3 that's getting applied here. And then if we take probability of B, we compute this, it's the probability of A intersect B plus the probability of A complement intersect B. And again, this is by axiom 3, and the fact that A intersect B intersect A complement intersect B is empty. So again, because this is empty, we can apply axiom 3 to get this. Because this is empty, we can apply axiom 3 to get this. And so we now have the probability of A, I'm just rewriting these equations separately, is equal to the probability of A plus the probability of A complement intersect B. And I have the probability of B is equal to the probability of A intersect B plus the probability of A complement intersect B. So this is a sort of just a standard routine set of tricks, which is we find expressions for the union of something in terms of things that are disjoint, or the expression for a set in terms of disjoint things. And therefore, when we compute the probability of this, it becomes the probability of the sums of the it becomes the sums of the probabilities of these two things and these two things, which is what we have down here. So now these are just two equations, and they seem to have something in common, right? Mm-hmm. So if we subtract, say, this equation from this equation, we'll eliminate this thing, this term. So we're going to subtract, and we get P probability of A union B minus the probability of B is equal to the probability of A minus the probability of A intersect B. But aren't we now just a step away from what we wanted to prove? I mean, in other words, can I just add probability of B to both sides? So the probability of the union of A and B is equal to the probability of A plus the probability of B minus the probability of their overlap. Mm-hmm. So this has certainly gotten more complicated than where we started, but the basic technique has stayed the same, which is find some useful disjoint union to express a set, an event, and then take probabilities and use axiom 3. In this case, we have the final step, which is to subtract that equation from that equation, producing our final result. I'm not sure I gave you enough room to write all that down, but hopefully you can fit it in
Make
there.
it- We'll make it work.
Okay.
We'll just shove it down.
Yeah, no, good.
I've learned to make things work.
Yeah. So, are you following this?
I am. I'm following the diagrams probably more so than I am what your formulas or your writing out.
Okay. But the diagrams are critical in a sense. Without knowing these things, then I can't do the rest of this.
How about you, Daisy and Dylan?
Yeah, I think I'm in a good spot, more or less.
Yeah, I like using the diagrams to follow along. I think that makes it
Yeah, that
a bit
visual
easier
really helps.
to visualize.
And look, yeah, in a sense, so I'm doing the proofs because I think it's worth seeing some of this stuff, but the message is what you seem to be grasping easily, intuitively, is that if I'm going to add these two guys together, I need to make sure I cancel out the overcounting that occurs by their overlap, which is what this is doing. And that's the main point of this. So if I want to find the probability of two events at once, I need to make sure that I can add the probabilities, but there may be some overlap in these events where they're both happening together, and I want to make sure that I compensate for that fact.
Mm-hmm.
And we'll see an example of this, with some, actual cards, say, where we see this issue.
Okay.
So, if I may ask a question on down the bottom of 5, if if I'm correct in understanding what this is saying, I'm not talking about answering the question. I just want to get my head wrapped around what's written here. So the probability of A intercepting with B, which is like your top diagram, right?
Yes.
To equal the probability of A and the probability of B, which is your second little diagram, correct?
Yeah.
Okay.
Yeah, you have to be careful here, though, because this notion of independence is not easily viewed in a diagram, in a Venn diagram. This is, in some sense, what sets probability apart from more general mathematical rules of area addition or volumes or something. This is sort of special to probability theory. And it's not something that you can see in a Venn diagram.
Oh. Because
I can't. I mean, in other words, I have difficulty visualizing what this would mean in a Venn diagram.
Okay, so in the book where it shows a diagram of A and B, and it's overlapping on page 241.
Yeah.
That overlapping section, is that what you're talking about here? Of the independence?
No.
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 Okay,
No.
all right,
No, that's what we've been using where we're looking at unions. But when we're talking about A and B occurring, the probability of A and B occurring together, we're not talking here about unions anymore. Their joint probability, it's called, if they're independent, is the product of their probabilities. And I don't really know how to visualize that. Perhaps there is a way, but I don't know how to show that in a Venn diagram. The intersection is something different.
all right,
In other words, yes, the intersection is that slice, that piece, that's not changing. But the probability of the intersection is what I don't see how to represent that in terms of areas there. It's somehow the product of the two areas, but I don't. What does that mean in this picture? I don't. That's what I don't see. So yes, we're still talking about that intersection, this slice here, this piece, but we're talking about a product of probabilities, and up to this point, we've been talking about adding probabilities. It makes perfect sense to add the area of this and add the area of this and take away the area of this. But when we start talking about the product of this and this is so I don't have any obvious way, and maybe it's just because I don't know it, but I don't have any obvious way of thinking about that in terms of Venn diagram regions and areas and so on.
but it goes on, moving on into, page 6.
Yeah.
It's talking about two events are independent of the occurrence of one has no effect on the probability of the occurrence of the other.
Correct.
And it's asking us to draw this Venn diagram. Well, if we draw a Venn diagram of what we're seeing here, A and B intersects. Correct?
Yeah, again, it's so what I'm asking you to do here is not to draw a Venn diagram that shows what independence is, but to use a Venn diagram to show that if A and B are independent, then A and B complement are independent. So again, it's not clear to me that the Venn diagram is going to give you insight into the geometry, if you like, of independence.
Okay, so to draw that diagram, though, you do have to have A and B intersecting, right?
Yeah.
And then you have to have A and B complement intercepting.
Yeah. So let's draw a picture. So again, yes, but that's going to just follow from. So here's. So just standard thing. We're going to do this again, and call this A, and call this B, and then this in here is A intersect B. And we've already decided earlier that for the probability of B anyway, that this was true. So it seems to make sense that it should be true. Well, actually, I'm doing something a little different, so hold on. So in this Venn diagram, we want to show A intersect B union. So A intersect B is this. Union A intersect B complement. Well, so we're taking sort of we're taking this picture and looking at its negative, in a sense. So B complement is, all this stuff. And if we intersect that with A, then we're going to get this. And And when we combine it with this, we get A back again.
Okay. So the B complement is everything outside
Of
plus
B.
the A. Everything outside B, which is outside, which includes A,
Yes,
right?
yes. Except for the part in here. Because that's in B too. Right? B is this. So everything outside of B is everything outside of this circle. But we're getting this back because we're unioning everything outside B with the stuff that's in the intersection of A and B. What we're forming is A intersect B, and we're unioning that with A intersect B complement. And this is A. Previously, we did this to find B. We took A complement and A and intersected those with B and took the union and found B. We're just flipping we're just replacing B with A here. So this is true.
So you're, okay. So you're, oh, I see what you wrote. Okay.
So what we're trying to show is the claim is that if probability of A intersect B is equal to the probability of A times the probability of B, then probability of A, what are we looking at? Yes, so here intersect B complement is equal to the probability of A, the probability of B complement. In other words, if A and B are independent, then so are A and B complement. So how would we go about proving this? Well, let's compute. So the probability of A intersect B complement well, we have this up here, right?
Right.
So that means this is equal to the probability of A minus the probability of A intersect B, right?
Yeah.
Okay, I see what you did.
Right, I just subtracted this from both sides up here, and I
Right.
find out what this is equal to in terms of these terms.
Right.
Okay? But by independence, the probability of A minus probability of A intersect B is the probability of A times the probability of B, right? That's what we're assuming going in, is that A and B are independent. You agree?
So, okay, so under the proof, the first line, you basically you were solving for the P. a
I'm
probability
solving for
of
this,
A.
yeah, in this,
You were
yes,
solving for that,
yeah.
okay?
And then,
the-
go ahead. Go ahead.
Well, and then the second line, you're solving for the probability of A, but then you're also taking into account A and B, probability
Yeah,
of
so
both.
I'm looking at this and saying, well, these are independent. A and B are independent, so this thing must be equal to the product. So, can I factor out the probability of A here?
Yes,
So, right?
Okay.
okay. So you're saying up there on your first line of your proof,
Yeah.
you're saying the probability of A intercepting with B. So what you're saying is A and B, you saying are independent?
Yeah, that's the claim. That's our claim, is that if we start with independence of A and B, we get independence of A and B complement.
Okay.
So this is assumed that I can go from here to here.
Because